Hello and welcome to a higher tier Edexcel video from November 2018. This is paper 1, the non-calculator version. So it was done about 2.5 years ago. Let's just cut to the chase. Let's have a look at all the questions, and sometimes I'll show you more than one way of doing the question. Just pick whichever way you feel works best for you. So question 1. Question 1, I have to work out the value of 3 to the 7 times 3 to the minus 2 all over 3 cubed. For this one, we just need to remember the laws of indices. So let's just do the top first. So the top, when we multiply and we've got the same base number, the big number, the 3, all we need to do, if we're multiplying, we add together the powers. So 3 to the power 7 multiplied by 3 to the power minus 2, that's going to be the same as 3 to the power 7 added to minus 2. But of course, all of this is over 3 cubed. So I'm just going to leave the 3 cubed as it is for now. So going one stage further, this power of 3, 7 add minus 2 is the same as just 7 minus 2, which is 5. And then we're going to divide that by 3 cubed. Now, when we're dividing involving powers, because dividing is the opposite process of multiplying, instead of adding the powers, we subtract the powers. So at this stage, we do the new power as 5 minus this bottom power, 3. So 5 minus 3. 5 minus 3 is 2. So it all boils down to just being 3 squared, and 3 squared is obviously 9. So that's the first question done. We're off and running. Let's have a look at question 2. We have a formula in which we need to substitute a value of v. So we're told here that v squared equals u squared, where we're told what u is. U is 12, we're told, plus 2as. So a, we're told, is negative 3, and we're also told that s is 18. So work out a value of v. If you notice it says a value, it's because we've got v squared. So when we square root something, we can consider both positive and negative. But anyway, let's just think about what v squared is. So it's u squared plus 2 lots of as. But of course, we were told that u is 12. So that's 12 squared plus 2 multiplied by negative 3 multiplied by 18. Just by substituting in the numbers we know. So we knew that u is 12. We were told that a is negative 3. And we're also told that s is 18. So 12 squared, you should know all the square numbers ideally up to 15, maybe even beyond. 12 squared is 144, so you can write that down straight away. This one here, remember BIDMAS, we're going to do the squaring and the multiplying first. We're going to leave this adding till last. So we've done 12 squared, which is 144. We're now going to do 2 multiplied by negative 3 multiplied by 18. Well, 2 multiplied by negative 3 is going to give us minus 6. And we're going to multiply that by 18. So what we're going to do first of all is just think about what it will be as a number and then attach the negative onto it afterwards. So just think of it for now as 6 times 18, or 18 multiplied by 6. There's various methods for multiplying, so I'm just going to use this fairly standard one, column multiplication. So 6 multiplied by 8, that'll give us 48. Put the 8 and carry the 4. Then the last thing we do is 6 multiplied by the 1. Now 6 multiplied by 1 is obviously 6, plus the 4 we're carrying gives us 10. So that gives us 108. But because it was a minus 6, we've got minus 108. So that's what 2 multiplied by negative 3 multiplied by 18 is. It's negative 108. So again here, we're adding a minus. Mixed makes minus. So adding a minus is the same as just subtracting. So it's the same as 144 take 108. I'll show you how to do this if you're a bit rusty or lacking in confidence. It's all good. So we can't do 4 take away 8 because the number we're trying to take away from 4 is bigger than it. So what we're going to do, we borrow next door from this 4. This 4 now becomes 3, and the number we borrow goes to the right hand side. So this 4 is now 14. We can now do 14 subtract 8. 14 take away 8 is 6. 3 take away 0 is 3. 1 take away 1 is nothing. So after all that, we have that v squared equals 36. Therefore v is going to be plus or minus the square root of 36. It says work out a value of v, so we can just probably go for the most obvious one and say let v equal positive 6. And that's all we need to do for that question. So v is either plus 6 or minus 6, but v being positive for 6, I would suggest is the most obvious option to go for. For part 2 of question 2, part B I should say, make S the subject of this equation. So, there are 2 main ways of doing this. Okay, so the first method I'm going to show is algebraic balancing. So I'm just going to call this a balancing method. Just how you'd normally solve any equation, really. So we want to make S a subject. All that means is we want S on its own. So I'm going to start with what we've got. I'm not going to do any work at this first step. The objective is to have S all on its own. As a first step, what we can do is subtract a u squared from both sides. So take away u squared from both sides of this equation. Gives us v squared minus u squared equals 2as. So 2as means 2 multiplied by a multiplied by s. So s is being multiplied by not just an a or a 2, s is being multiplied by 2a. The opposite of multiplying by 2a is to divide by 2a. So if we divide both sides by 2a, the 2a on the right hand side will cancel, leaving us with just s, which is what we want. So we then get v squared minus u squared all over 2a equals s. But we're still not done. If s is a subject, we need to write it s first. So we just keep it exactly the same, but reverse the order. And we say that s equals v squared minus u squared all over 2a. Method B is a function machine. So we start with what we're trying to make the subject. So we start with s, pop it in a box, and then think about step by step what happens to s so that we arrive at v squared at the other side of the equation. So s comes along, the first value or thing it's interacting with is this a and the 2. The first thing that happens to the s is it gets multiplied by 2a. So first off we multiply by 2a. At this stage we have 2as. Then the u squared comes along and adds itself on. So now we add u squared. And nothing else happens on this right hand side. After we multiply by 2a to give 2as and add a u squared, we get u squared plus 2as, which is what v squared is. And so all of this lets us arrive at v squared. Now what we could do is we go the opposite way, doing the opposite things, rewinding this whole process back until we get to what S is. So on this side now, we start with what we ended up with. We start with V squared. But now we're going to trace our steps backwards. So at this stage, look what happened before. Before we added u squared. Because we're now going backwards, we're going to subtract u squared. So at this stage now, we started with v squared, we've subtracted u squared. So going into this next step, we've got v squared minus u squared. At this step, in the original method, we were multiplying by 2a, but now because we're going the opposite way, we'll do the opposite thing, which means we'll divide by 2a. And so the final step, we have this v squared minus u squared, but it's now been divided by 2a. So we end up with v squared minus u squared divided by 2a. But we've got back to the beginning, so whatever is in this box must be what s was to begin with. In other words, s equals v squared minus u squared over 2a, which again we can write down. So whichever method makes more sense to you, feel free to use that and practice that to get stronger with using it. Question 3 next. We have a bonus of £2,100 which is being shared by 10 people who work for a company. 40% of the bonus is shared equally between 3 managers. The rest of the bonus is shared equally between 7 salesmen. And one of these salesmen says, if the bonus is shared equally between all 10 people, I would get 25% more money. Is the salesman correct? You must show how you get your answer. So, let's just think about what's happening here. For £2,100 is being shared, but 40% is gone to these managers, so essentially it's a percentage problem. Before anything happens to a number, we always start with 100% of it. So 100% of this starting figure is the starting figure itself, 2,100. We could work out what this 40% of the bonus is, because then we'll work out how much the managers have got. So what we can do now is we could quite easily go from 100% to 10% by dividing by 10. So it looks like, in a way, we're just knocking a 0 off. So we can do the same on this side. So 10% gives us £210. We're not literally knocking a 0 off, it's just the effect of dividing a whole number that ends in 0 by 10. So the actual process we've done is we've divided by 10. Now we've got 10%, we could easily work out 40% by just multiplying this by 4. 10 times 4 gives us 40, so we do the same to this 210. So 210 multiplied by 4, that's going to give us 840. So that's what the salesman managers are getting. So these 3 managers are getting in total £840. So I'm just going to make a note to myself that that's what the 3 managers are getting between them. So if the 3 managers are getting 40%, that means that the 7 salesmen are getting the other 60%. So we can take the 10% and multiply by 6 to work out what 60% is. So let's do that now. Obviously here we multiplied by 4, but if we want 60%, we can multiply by 6. An alternative thing we could have done is we could have taken 2,100 and taken away this 840 to work out what these 7 salesmen have left between themselves. So there's often, as you'll know by now, a few ways of doing things with maths. Anyway, here, If we do 210 multiplied by 6, well, 200 times 6 is 1200, and then this £10 times by 6 gives us 1260. And so the rest of the bonus is this £1260, and that's going to be shared between these 7 salesmen. So, because it's being shared between 7, we can say that each salesman will get 1260 divided by 7. So let's see what that gives us. So first of all, can we divide 7 into 1? Well, no, we can't. So the remainder for that one is 1, which we move next to this 2. So this 2 is now 12. Next, can we fit 7 into 12? Well, yes we can. 7 goes once into 12, with 5 left over, because 12 minus 7 is 5. Next, we see if we can fit this 7 inside 56. Well, 7 squared, 7 times 7 is 49. An extra 7 would take us to 56 exactly. And then 7 into 0 doesn't go. It goes 0 times, but to complete the division, we still write that 0. So each salesman gets £180. So we can write that. We can now compare what each salesman gets with what the salesman is saying. So one of the salesmen says, if the bonus is shared equally between all 10 people, I'd get 25% more money. Well, if the bonus was shared equally between all 10 people, how much money would each person get? Now that's quite easy to work out. If it was equally shared, that would be 2,100 divided by 10, which is just £210. So the salesman seems like he might be right. He's definitely getting more money if it was equally shared. This salesman would have got £210 instead of 180. So he would be getting more, but would he be getting 25% more? So what we need to do now is to work out 25% more money than what he's currently getting. And the way we do this is we base the percentage off the original amount that's being received. So this amount is £180. So if he were to get 25% more money, this £210 would equal 180 plus an extra 25% of 180. So 25% of 180. 25% is the same as a quarter. So a quarter of 180 means we can half it, then half it again. Do division if you want to check, that would be £45. So 25% more money would be 25% of 180, which is £45. However, £210 is actually more by only £30. That's more than 180. By £30, but 25% more. Would have been £45 more. So is the salesman correct? So about this mess actually, this isn't the best well presented of questions. So is the salesman correct? No. Salesman is incorrect. He gets more money. He would get more money, he'd get £30 more. But 25% more would have been £45 more. So although he's getting more money, it's not 25% more, it's actually 1/6 more. It's 16.67-ish more percent. So that's one way of doing it. There are other ways to do this question, but I'll just leave it there for now. So that's question 3. Question 4. This is one of these newfangled ratio type questions and proportion. So we're told it would take 120 minutes to fill a swimming pool using water from 5 taps. For question part A, how many minutes will it take to fill the pool if only 3 taps are used? So let's just imagine this now. Imagine 5 taps running as fast as they can to try and fill up a swimming pool. So let's just draw in these 5 taps. Okay? And so each one's running for 120 minutes. So this tap here has been running for 120 minutes. The second one, 120 minutes, and so on. They've all been running for 120 minutes. So what's this equivalent to for one tap just being left on? 120 minutes for one tap, plus 120 minutes for a second tap, and so on and so on. That's equivalent to 600 minutes of water for one tap. So if we need the equivalent of 600 minutes for one tap, how many minutes would it take to fill the pool if this burden of one tap was shared by 3 taps? Okay, well, if it takes 600 minutes for one tap, but that load is being shared by 3 other taps, we divide the 600 minutes needed for one tap by 3. 600 divided by 3 is 200. So for 3 taps, it would take 200 minutes. 200 plus 200 plus 200 would be 600, which would be the same amount of time needed, essentially, for if it were 5 taps running for 120 minutes, or the same amount, in theory, as one tap going for 600. Now state one assumption you made in working out that answer. Keep it very simple, it's only 1 mark. In reality, are all taps identical? No, they're not. In this mathematical model, are we going to overcomplicate it by thinking some taps are different than others? No, we're not. And so one assumption we've made, which is a fairly safe assumption, is we're assuming that water comes out of each tap at the same rate, or something along those lines. That's all we need to say to secure that extra mark for question 4. Question 5, we have an estimation question. A plane travels at 213 miles per hour. Work out an estimate for the number of seconds it takes to travel 1 mile. So first of all, I'm going to just mention there are 2 main ways we could do this. So method A and method B. Well, method A, probably the most common and tempting one, but not always the easiest, is to consider this as a speed, distance, time equation, with which we can use the magic formula triangle SDT. Speed equals distance over time. Sausages don't talk is one of the silly ways of seeing this remembered, which does work. So what do we actually need to calculate? So what we've got here is it's asking us for an estimate for the number of seconds. Now, number of seconds, that's a measure of time. So we can use this formula triangle. We cover up what we want to find out. We want to find out time, so we can literally just cover this up, and whatever's left tells us what to do. So time equals, well, we've got d left on top and s on the bottom with a line between them. So this means distance divided by speed. So the distance is it's going to travel 1 mile. And so we put this one in. And the speed, we're told it's 213 miles per hour. So not the most easy number to work with. So 213 is a speed, but that's just really awkward. But this is where the estimation comes in. It says estimate, so we're allowed to round these numbers if we need. So squiggly line, which means approximately equal to. I can change 213 to an easier number if I wanted. So as long as it's not too far away, it's fine. So imagine £213. Let's imagine that your parents or somebody you know promised you £213 as a gift or a debt or whatever, and because you know them said, I've not quite got that, could I give you £200? You probably wouldn't be too disappointed. All I'm trying to say is £200 is fairly similar to 213, so I could call the 213 200. It's very roughly the same thing. So this fraction is much nicer than that one. So what units of time are going to come out? Well, think about the units we've put in. We've put in miles, but the units of time we're mentioning here are hours. So that's going to be 1/200th of an hour. Okay. So it doesn't really get us anywhere yet because we want to work out the number of seconds. Okay. So what we need to do here is think about how many seconds in an hour. Well, 1 hour equals 60 minutes. But each one of those minutes is in itself 60 seconds. So that's 60 lots of 60 seconds. So 6 times 6 is 36. Add on the 2 zeros. We can see that an hour is 3,600 seconds. So 1/200th of an hour means 1/200th of 3,600 seconds. We can now simplify this down. So we're dividing by 200, but we're multiplying by 3,600. So if we put this fraction as 3,600 over 200, we'd have 2 zeros at the end that cancel with the 2 zeros there. And so it becomes a half of 36. A half of 36 is 18 seconds. So that's our estimate for how many seconds the plane would take to travel 1 mile. Doesn't sound like much, but then planes do travel very fast indeed, so that's quite possibly absolutely accurate. Method B, it's more like a build-up method. So method B, we're just basically considering speed as a ratio of distance travelled to the time taken. So we're told it travels 213 miles per hour. Okay, so that means 213 miles in 1 hour. Now we can round this 213 miles, that's about 200 miles. In 1 hour. But again, we worked out from before that 1 hour is the same as 3,600 seconds. So I'm going to replace this 1 hour with 3,600 seconds. But we want to work out how long it takes to travel 1 mile, not 200. So what we can do here is just divide both the mile value and the time value by 200. $200 divided by 200 gives us obviously 1 mile. And 3,600 divided by 200, well, 36 divided by 2 is 18. and then the zeros again will just cancel. So 1 mile in 18 seconds. So we can do this in terms of proportional reasoning rather than thinking of it in terms of a formula. So 18 seconds again is our answer for an estimate of time. Finally, it says, is your answer to part A an underestimate or overestimate? Give a reason for your answer. Well, here what we've done, we've rounded down how far the plane travels in 1 hour. It actually could travel 213 miles in 1 hour, but we've estimated it down to 200 miles in an hour. So our estimate has slowed the plane down. We're estimating it to be slower than what it actually is. So because our estimate is based on the plane travelling slower than in reality, that means it takes longer to cover that distance than what it actually would do in reality. So 18 seconds is actually an underestimate. Question 5, we have an estimation question. A plane travels at 213 miles per hour. Work out an estimate for the number of seconds it takes to travel 1 mile. So first of all, I'm going to just mention there are two main ways we could do this. So method A and method B. Well, method A, probably the most common and tempting one, but not always the easiest, is to consider this as a speed, distance, time equation, with which we can use the magic formula triangle SDT. Speed equals distance over time. Sausages don't talk is one of the silly ways of seeing this remembered, which does work. So what do we actually need to calculate? So what we've got here is it's asking us for an estimate for the number of seconds. Now, number of seconds, that's a measure of time. So we can use this formula triangle. We cover up what we want to find out. We want to find out time. So we can literally just cover this up, and whatever's left tells us what to do. So time equals, well, we've got d left on top and s on the bottom with a line between them. So this means distance divided by speed. So the distance is, it's going to travel 1 mile. And so we put this one in. And the speed, we're told it's 213 miles per hour. So not the most easy number to work with. So 213 is a speed, but that's just really awkward. But this is where the estimation comes in. It says estimate, so we're allowed to round these numbers if we need. So squiggly line, which means approximately equal to. I can change 213 to an easier number if I wanted. So as long as it's not too far away, it's fine. So imagine £213. Let's imagine that your parents or somebody you know promised you £213 as a gift or a debt or whatever, and because you know them said, I've not quite got that, could I give you £200? You probably wouldn't be too disappointed. All I'm trying to say is £200 is fairly similar to 213, so I could call the 213 200. It's very roughly the same thing. So this fraction is much nicer than that one. So what units of time are going to come out? Well, think about the units we've put in. We've put in miles, but the units of time we're mentioning here are hours. So that's going to be 1/200th of an hour. Okay. So it doesn't really get us anywhere yet because we want to work out the number of seconds. Okay. So what we need to do here is think about how many seconds in an hour. Well, 1 hour equals 60 minutes. But each one of those minutes is in itself 60 seconds. So that's 60 lots of 60 seconds. So 6 times 6 is 36. Add on the 2 zeros. We can see that an hour is 3,600 seconds. So 1/200th of an hour means 1/200th of 3,600 seconds. We can now simplify this down. So we're dividing by 200, but we're multiplying by 3,600. So if we put this fraction as 3,600 over 200, we'd have 2 zeros at the end that would cancel with the 2 zeros there. And so it becomes a half of 36. A half of 36 is 18 seconds. So that's our estimate for how many seconds the plane would take to travel 1 mile. Doesn't sound like much, but then planes do travel very fast indeed, so that's quite possibly absolutely accurate. Method B, it's more like a build-up method. So method B, we're just basically considering speed as a ratio of distance travelled to the time taken. So we're told it travels 213 miles per hour. Okay, so that means 213 miles in 1 hour. Now we can round this 213 miles, that's about 200 miles. In 1 hour. But again, we worked out from before that 1 hour is the same as 3,600 seconds. So I'm going to replace this 1 hour with 3,600 seconds. But we want to work out how long it takes to travel 1 mile, not 200. So what we can do here is just divide both the mile value and the time value by 200. (200) divided by 200 gives us obviously 1 mile. And 3,600 divided by 200, well, 36 divided by 2 is 18. And then the zeros, again, will just cancel. So 1 mile in 18 seconds. So we can do this in terms of proportional reasoning, rather than thinking of it in terms of a formula. So 18 seconds, again, is our answer for an estimate of time. Finally, it says, is your answer to part A an underestimate or overestimate? Give a reason for your answer. Well, here what we've done, we've rounded down how far the plane travels in 1 hour. It actually could travel 213 miles in 1 hour, but we've estimated it down to 200 miles in an hour. So our estimate has slowed the plane down. We're estimating it to be slower than what it actually is. So because our estimate is based on the plane travelling slower than in reality, that means it takes longer to cover that distance than what it actually would do in reality. So 18 seconds is actually an overestimate. It's an overestimate because we've actually rounded the number of miles it travels in 1 second down. The time's an overestimate because in reality the plane's actually quicker, so it takes less time, because 213 miles an hour is quicker than what we've rounded it to, which was 200 miles per hour. Question 6, simultaneous equations. A fairly standard question, really. Solve these simultaneous equations. So there's two approaches if we have a pair of linear simultaneous equations. So just to recap, one approach is elimination, and the other approach is substitution. So when we eliminate, what we want is to have the same number of x's or y's in both the top and the bottom equation. At this stage, it doesn't matter about the signs in front, just focus on the number purely. And so think about one x as like so, and that y as being a 1y. So it's your choice. You can try to eliminate the x's or the y's. I personally am going to go for eliminating the y's. So what I'm going to do here is I'm going to multiply the top equation by 3, and the bottom equation I'm going to leave as it is. So if I do that, 5x multiplied by 3 becomes 15x, y times 3, it becomes 3y, and 21 multiplied by 3 becomes 63. I'll leave the bottom one as it is, so x minus 3y equals 9. So now, we've got the same number of y's. We've got a 3y on the top, which happens to have a plus in front of it, and a 3y on the bottom, which happens to have a minus in front of it. When the signs are different, we add the equation. So what we're going to do here is we're going to add the top equation to the bottom equation. And what we get when we do that, when we add the x's, 15x's plus 1x gives us 16x. 3y plus minus 3y gives us no y's at all. And 63 plus 9 gives 72. So therefore x is going to be 72 divided by 16. So we can simplify this down somewhat. So for example, both top and bottom can be halved, so we can get 36 over 8. We could half again. In fact, it'd be quicker if we just divided by 4, if you can spot that. Dividing both top and bottom by 4, that gives us 9 over 2, which, if you want to, is 4.5. We then substitute this value into one of the original equations. So if I call this, for example, equation 1 and equation 2, the easiest is probably equation 2. So I'm going to sub x equals 4.5 into the bottom equation, into equation 2. So what do we get when we do this? So x minus 3y now becomes 4.5 minus 3y. Equals 9. If we subtract 4.5 from both sides, we get minus 3y equals 4.5. Then if we divide by minus 3, we can see that y equals 4.5 divided by minus 3, which gives minus 1.5. So the solution to these simultaneous equations is that x equals 4.5 and that y equals minus 1.5. And if in doubt, check them in by putting them into one of these starting equations, and you will see, if there's time, that they will generate the correct answers for both. Now, substitution is generally seen as being less popular, and it is a bit more awkward. But let's just show you so you know which method you prefer, just in case this one does appeal to you. So, for example, I just need to make either x or y the subject for one of these equations. So if I pick the bottom equation and make x the subject, I can see that x equals 9 plus 3y, just by adding 3y to both sides. So what I can do now is I can substitute this in to equation 1. So let's do this now. So I'm going to substitute x equals 9 plus 3y into equation 1. And it would have worked if I'd made y the subject and substituted that into a different equation. So it was more than one way of doing it. I just picked x because I spotted here. If I just add 3y to both sides, it's quite an easy thing to make the subject. So now, equation 1. 5x becomes 5 lots of 9 plus 3y. Plus y equals 21. So next, if I expand this out, 5 times 9 is 45. 5 times 3y is 15y, and plus y gives 21. Simplify it. So 45 plus 16y because 15y plus 1y gives us 16y. That equals 21. Next, if we get 16y on its own by subtracting 45 from both sides, okay, we see that 16y is 21 minus 45, that's minus 24. But if we divide both sides by 16, we see that y equals minus 24, divide by 16, which can simplify. For example, if we divide both sides, both top and bottom by 8, we get minus 3 over 2, which is fine, or we can say it's minus 1.5. And again, you're noticing now we've got the same value for y here as we did in the first method. But just to follow it through, so you can see that it does definitely work, we can now take this value of y and substitute it into either 1 or 2. So if I now I'm just going to pick equation 2 because it's easier. Well, in fact, I can pick this one. That's even easier. So I'm going to sub that y is minus 1.5 into x equals 9 plus 3y. So out will pop x. So x equals 9 plus 3 lots of minus 1.5. Well, 3 times minus 1.5 is minus 4.5. And if I'm adding that minus, it's the same as just subtracting 4.5. And 9 take 4.5 leaves me with 4.5. So again, exactly the same solutions as before, just a different method. Use whichever one you'd prefer. Question 7. We have a diagram showing a square ABCD with sides of length 20 centimeters, and we also have a semicircle and an arc of a circle inside. So AB, from the bottom, is the diameter of a semicircle. A to C is an arc of a circle with a centre at B. So actually, from A to C, that's an arc of a quarter circle. So if that's centred at B, the full circle would be something like this, going slightly below the page and back up again. We need to show that the area of the shaded region as a fraction of the overall total square is pi over 8. So what we need to think about here, would suggest, is how we can actually think of this shaded area in relation to this quarter circle and that semicircle. Okay, so the way I'm thinking of it, which is just one way, is I'm imagining that this corner bit used to be a full circle, a full quarter circle, like so. But then that bottom bit, which I've called in red, was cut away and removed. So you can think of, in one sense, this shaded area as being the quarter circle, this whole thing, with this semicircle cut out from underneath it. So now what we need to remember is, how do we work out the area of a circle? Well, start with circumference, which is pi times diameter, and area is pi r squared. Chicken pie's delicious, apple pies are too. Chicken pie comes first because that's your main course, apple pie is a dessert. Okay, so chicken pie and apple pie, to make sure you don't mix the C and the A up in these formulas. That sounds a very silly way of remembering it, but it's surprisingly useful. Circumference is pi times diameter, area of a circle is pi times radius squared. If you can remember that without having to remember any other way of thinking about it, that's great. If you do need a hand, remember, chicken pie is delicious, apple pies are too, and if you are vegan or vegetarian, be my guest to substitute a cherry pie in place of the chicken. So, now using this idea here, the shaded area is a quarter circle minus a semicircle. This quarter circle has an area of 1/4 of the area of what would have been for full circle. Okay, so the full circle, if that was its centre here, its radius would have been 20. So it's a quarter of pi times 20 squared. Okay, so it's a quarter of pi, 20 squared, 20 times 20. Well, 2 times 2 is 4, then add the 2 zeros, we get 400. A quarter of 400 is 100, so that's 100 pi. The semicircle here, its diameter is 20. So what we need to think about now is what its radius would be. So radius is always half of what the diameter is. So if the diameter is 20, the radius is 10 centimeters. So the area of this one will be, because it's a semicircle, it's going to be half of pi times 10 squared. Now, 10 squared is 100. Half of 100 is 50. So that gives me 50 pi, like so. So 100 pi here for this one. Quarter circle has an area of 100 pi. The semicircle, we've calculated, has an area in terms of pi of 50 pi. So 100 pi minus 50 pi gives just 50 pi. So the area of the shaded region is a quarter circle of 100 pi minus the semicircle, which has an area of 50 pi. So the shaded area is 50 pi. So we can now fill this in. So the shaded region, whoops, that's not what I wanted to do at all. Apologies. So the shaded region over the area of the square the shaded region is 50 pi, so we can fill this in. But we still need to work out the area of this square. So that's actually, luckily, probably the easiest part. So we're told the length of this square from A to B is 20. So the height will be 20. Remember, all sides of a square are equal. So the area of the square is just going to be 20 times 20, which is 400 cm squared. So we can fill this in and complete the last part of the puzzle. So the area of a square is 400 cm squared. So if we now fill this in into the fraction, we can now see that this can be simplified. 50 into 400. So how many times will 50 fit into 400? It will go in 8 times. Another way we can think of it is we can divide both top and bottom by 50, which will leave us with pi over 8, because 400 divided by 50 leaves us 8. And that's what we wanted to prove, so we can stop and we're done. So pi over 8 is what we've got, so we're done. Question 8, we're asked first of all to write down the exact value of tan 45. Now there's two main ways of doing this, apart from just remembering the table of exact trig values, which no doubt your teacher may have shown you already. So there's just a way of just knowing it. If you just know it, the answer is 1. But I'm going to try and show you how you could sort of derive it by just thinking about the graph of sine. And as well as that, I'm going to show you a second method where you can think of it in terms of a special triangle. So the first one, in terms of just deriving them yourself, is remember we have sin, cos, tan, SOHCAHTOA. So let's just think of values of sine. Okay, so we'll go sin, cos, tan, sine, cosine, tangent. And there are 5 main angles where we need to find out the exact trig ratios for these ones. So I'll just do a little table here, and I'll just draw in 5 columns. So 1, 2, 3, 4, 5. So the angles you need to consider are 0, 30, 45 is the middle one, 60, all the way up to 90. Now, if you remember the graph of a sine, just the beginning of the graph really, what happens to the graph of sine as x moves from 0 to 90? Well, as long as you remember just the graph of sine, you can work out the others. So sine goes up and peaks at 90, and it peaks at a value of 1. Okay, so that value when sine is 90 is 1. So as you can see, it's rising from 0 to 1. So we start with 0 and we go up to 1. And the numbers we stop off at in between, as we go from 0 all the way to 1, are going to involve fractions, are going to involve halves. Okay, so these halves get bigger. So the first one is simply half of 1, 1 half. So you can think of that as being root 1. The next one is root 2 over 2, and this one is root 3 over 2. So actually, weirdly, but nicely to think about, that's root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, and root 4 over 2 would give you 1. So as long as you can remember that and derive that for sine, you can do the others, because cos is just for sine ones in opposite order. So we do this for sine but in reverse. So 1 root 3 over 2, then root 2 over 2, then 1 over 2, and finally 0. Then we work out the sine ones, so we work out the tan ones, I mean to say, by doing sine divided by cos. So we just do the top row divided by the middle row. So the first one, 0 divided by 1 is 0. This one here, a half divided by root 3 over 2, that just gives us 1 over root 3. This one, for 45 degrees, root 2 over 2 divided by the same thing. Anything divided by itself gives us 1. This one, root 3 over 2 divided by a half is the same as root 3 over 2 multiplied by 2. That gives us root 3. And this one, 1 divided by 0 is undefined, so we'll leave that one out. But ultimately, we want tan 45, which is 1. So therefore, we just say tan 45 is 1. I appreciate this is a 1-mark question. I wouldn't expect you to do this. I'm just saying, please learn this in advance, so that when you do come to a question which is only 1 mark, you'll know how to do this quite quickly. I'm not suggesting you spend a few minutes doing this in a test unless you really have the time to. Another way we can make sense of tan 45 being 1 will be to construct a special 45, 45, 90 triangle, like so. So it's a right-angled triangle with 2 angles which are 45 and 45. It's isosceles, and what I'm going to do here is I'm going to define the base as being 1 and the height as being 1. And if we do that, using Pythagoras, this hypotenuse will be 1 squared plus 1 squared, square rooted, so this longest side will be root 2. We can then pick either one of these 45-degree angles and think about how tan is defined as a trig function. Well, it's the opposite side divided by the adjacent. So whichever 45 we pick, the opposite side will be 1, and the adjacent side will be the other side that isn't the hypotenuse, which will also be 1. So we're going to get 1 divided by 1, which is 1. Using this triangle, you can also find sine and cos of 45 degrees too, which is pretty useful. Let's have a look at part B. So here we've got a right-angled triangle, and we are asked to work out the value of x. So if we work out the value of x, we need to think about these triangles SOH, TOA. Okay, so we know some sides. We know here this side is 4. So let's label on these sides. The side opposite to the angle, label O for opposite. So I don't want to know the opposite. Okay, I want to know this side x. X is the longest side. The longest side is h. So I'm interested in side h because I want to find out what x is. So I'm going to colour in h on these triangles just as a clue to myself that I need to know how to work these out. The other side I know, if it's not the O or H, it's A. So the side I know over here is the adjacent side. So the adjacent side is 4. So wherever I see an A, I colour it in. I want to work out x, which is hypotenuse. Of these SOH, or TOA triangles, I pick the one which has been most coloured in, essentially. So it needs to include the side I know and the side I want to know. So it needs to include A and H. And the only one of these triangles that includes the A and the H is K. Okay, I'm not trying to find the angle, so C in our case stands for cos of the angle. So we're just going to use this triangle here. So cos of the angle we know, so cos 60, equals the adjacent side, which is 4, divided by hypotenuse, which is x. This can be rearranged, and in fact we can use this triangle itself to help us rearrange. Just cover up what we want to know. So cover up the h. H is A divided by cos of our angle. So x is going to be 4 divided by cos 60, which you could have got by rearranging this as well. But what's cos 60? Well, fortunately, we've been told what this is. Cos 60, we're told in the question, is 0.5, so we can fill this in. So 4 divided by 0.5. If you're dividing by a half, it's the same as multiplying by 2. Now, if you're not sure if you'd be able to see that in a test or exam, just multiply top and bottom by 2. And if you do that, 4 multiplied by 2 gives you 8. 0.5 times 2 is 1, and 8 divided by 1 is just 8. So we know, therefore, that x must be 8 centimetres. Question 9. So we have a cumulative frequency curve of times that 48 trains left a station on Monday. So it records information about the number of minutes the trains were delayed, correct to the nearest minute. So the next thing we need to do is to think about the question. So the question part A, we're told the shortest delay is 0 minutes. The longest delay was 42 minutes. On the grid below, draw a box plot for the information about the delays on Monday. Now, for a box plot, there's a few things we need to know. A box plot consists of 5 vertical bars, essentially. The first bar is representing the smallest value, in this case the shortest delay. The shortest delay was 0 minutes, so what that means we do is we just draw on a vertical line like so, where we see 0. As well as that, another vertical line we draw is for the biggest value, in this case the longest delay. We're told that's 42 minutes, so we go to 42 and draw a vertical bar at 42. As well as that, what we need to do is we need to work out the median and the quartiles. So there's 48 trains in total. That's our clue, really. 48 trains. So median means halfway. So we half this number of values. 48 divided by 2 is 24. So therefore, median is the 24th value. And we find this by reading it off on the graph. And so what we need to do here is we find 24 on the vertical axis. So 1, 2, 3, 4 here. We read off and go along until we hit the curve. And when we do, we read down and we see that that's 10. So the median is 10. So based on that, we do a third vertical line at 10. And that represents the median. For also other things, we need to draw in the quartiles. So quartile, the clue is in the name. We need to do a quarter of 48. So 48 divided by 4 is 12. And that therefore tells us that the lower quartile, LQ, is the 12th value. So it's a similar process as before. We just find where the 12th value is, and we read along and then off. So 10's here, 11, 12 is over here. So read off, and then down when we hit the line, and that gives us a value, I hope you can see, of 4 minutes. And so we just add this in as well. So the 12th value is 4 minutes. So therefore we add this in as a vertical line at 4. Finally, what we do, we've got the lower quartile and the median, we need to work out the upper quartile. So the lower quartile is your first quarter. The upper quartile will be 3 quarters, which is 3 times 1 quarter. So if lower quartile is a 12th value, the upper quartile will be the 3 times 12th value, which is the 36th value. And again, we just read off and along to find this one. So 30, 35, 36 is here. So read off and along like so. And we get exactly 20. So that's our final line that we add in for our box plot. So we add in a final vertical line at 20. And finally, to complete the box plot, the 3 middle lines, we draw a line from the top of the first to the top of the third, and from the bottom of the first to the bottom of the third one. That makes our box. And finally we extend to the ends to make the whiskers. Now I'm not saying you need to do these in the colours I have, I'm just doing the colours differently so you can see the significance of these 5 values. So red, shortest delay. Purple here, lower quartile. Green, the line through the bar, is the median. Black line for the upper quartile. The blue line at the very end for the maximum value. Part B, we need to see how these train delays compare for Tuesday. So we've now got a box plot below giving information about the delays on a Tuesday. Part B asks us to compare the distribution of the delays on Monday with the distribution of the delays on Tuesday. So let's remind ourselves of our box plot from Monday, which we've just done in the previous part. Okay, so that's what we had. Now, to compare box plots, we need to compare two different things. So, one thing we need to compare is a measure of spread. The main thing for a measure of spread is the interquartile range. The interquartile range for box plots is essentially the length of the box in the middle. It's the upper quartile minus the lower quartile. So for Monday, the interquartile range is 16. For Tuesday, the interquartile range is 17 minus 6, which is 11. We also need to compare a measure of the central tendency. So for this one here, we need to compare an average, and the average we're going to use is the median. So what's the position of the median for both? Well, the median for Tuesday is 8, the median for Monday was 10. So based on the medians and the interquartile ranges, we compare these statistics for both. So two comparisons, 2 marks. So first of all, comparing the medians, we can say that the median delay time for Monday was greater than the median delay time on Tuesday. That's because 10 minutes is greater than 8 minutes. So on average, if you like, trains were delayed a bit longer on Mondays than Tuesdays. And if you can, it's probably worthwhile comparing the distributions in context. So comparing the interquartile ranges, you could just say, I suppose, the interquartile range on Monday is greater than for Tuesday, but the interquartile range is a measure of spread. The smaller the interquartile range, the more consistent the data is. So because the interquartile range is smaller on Tuesday and greater for Mondays, we can say that the delay times were more consistent on Tuesdays than they were for the Monday, because the interquartile range is smaller on Tuesday than it is for Monday. Finally, for part C, Mary's saying here that the longest delay on Tuesday was 33 minutes. And she's saying then that this means that there must be some delays between 25 minutes and 30 minutes. So is she right? Well, let's just think about this. She's saying there has to be some delays between 25 and 30. So she's saying some need to be delayed between here. Whoops, that's 20, my mistake, silly me. Between 25 and 30, she's saying there should be some delays there. Now, this doesn't really tell us much, because if the longest delay was 33 minutes, what we do know is that between this end of the box up to the maximum value, the distance between the upper quartile and the maximum value, that's your top quarter of the data. So this is going to be 12 trains. So the 12 most delayed trains must be delayed for somewhere between more than 17 minutes, but less than 33, or no more than 33, I should say. But why should any train necessarily be delayed between 25 and 30 minutes? I mean, maybe they were, but how can she know that? Do they have to be delayed in those times? Not necessarily. It could be that all these 12 trains at the upper end here were delayed maybe between 17 all the way up to 25, but not including 25, and maybe just more than 30 minutes delayed up to 33. So they could have had delays in this yellow region or green, or both, but not in the red. So Mary isn't necessarily right. So what we need to say here for Mary is something along these lines. So no, Mary's not right. The upper quartile's 17 here, so a quarter of the trains, which is 12 of them, must have been delayed for between 17 and 33 minutes. However, these delays may all be either between 17 and 25 minutes, this bit in yellow I've coloured in, or they could have been delayed between 30 and 33 minutes, this green bit I've coloured in. There's no saying that any were delayed in between 25 and 30. They might have been, but she's wrong to say they must have been. Not necessarily, Mary. So that's all we need to do for question 9. So, question 10. We have to simplify x minus 1 over 5 brackets x minus 1 squared. Now, the trick here would be to write out this second bracket on the bottom twice. So at the top we have x minus 1, You'll see why I'm putting it into brackets in just a moment. On the bottom, I can rewrite x minus 1 squared as x minus 1 times x minus 1 again. So by doing that step, I can see that I've got a similar thing on the top and the bottom of the fraction. I have x minus 1 on the top, and on the bottom I have a product of three different things, and two of them are x minus 1, so I can cancel one x minus 1 on the bottom with the x minus 1 on the top. So essentially I can divide both top and bottom by x minus 1. If I divide the top by itself, that obviously just gives me 1. And on the bottom, I have 5 lots of x minus 1. If you really wanted to, you could write the bottom as 5x minus 5. You could write it in expanded form, but as it is, that's fine to receive full credit. So we can leave it like that, and we're done. Part B, factorise this one fully. So the key word here, and the examiner's actually been quite nice. To factorise fully implies that they might make a mistake, you may make a mistake where you only factorise it partially. When it says factorise fully, that's often a clue that to fully factorise it will require 2 or more steps. So what could the first step be? Well, looking at the numbers, 50 and 2. Both of these are multiples of 2, so I can factorise out a 2 straight away. So I've got 2, I want 50. What do I multiply 2 by to get 50? I need 25. Minus, so stick a minus in. I've got a 2. I need a 2, sorry. I've already got a 2, so I don't need to multiply by any other numbers. But I just need a y squared on the end. So that would be a common mistake to leave it like that, but actually we can go one step further. Because if you notice these brackets here, 25 is a square number, and y squared is a perfect square. That's y times y, and this is 5 times 5. So here what we have, because it's one take away the other, this is a case of difference of 2 squares. So we can, luckily, go one step further. So we'll leave the 2 as it is, put this bracket here, for 25 minus y squared. We put the square root of both, added, and the square root of both minused. And the last thing, for y, has to be the thing which comes after the minus sign in the initial unsimplified difference of 2 squares expression. So that's how we do that one, and that's the final step, luckily. So not too hard, as long as you remember both steps, and do bear in mind the wording of the questions. Read it carefully. You'll often see little clues slipped in, like here. Factorise fully, that's a hint that you need 2 steps, not just for 1. Question 11, we have Jack and Sadia working for a company that sells boxes of cereal. So it wants to have a special offer, and both Jack and Sadia have these ideas for what the special offer could be. So Jack's idea is to put 25% more cereal into each box, but don't change the price. So he's basically saying, you know, it's like a 25% extra free sort of deal. Whereas Sadia's saying, reduce the price, but don't change the amount of cereal in the box. Now, Sadia, we're told, she wants to have the same value for money as Jack's idea. So if that's the case, by what percentage does she need to reduce the price? The weird thing, in my opinion, about this question is we're talking about a physical thing, boxes of cereal, and money, but we're not told anything about what the actual size of this box of cereal is, or what the standard price was. So what I'm suggesting we do here is to make up the starting price. So make up the standard size and price. Then we've just got something tangible to work with then. Now you could do this method purely algebraically, but I think that is a bit harder because it's more abstract. So when you make up numbers, please make your numbers easy to work with, okay? Don't need to be realistic necessarily, but it does need to be realistic. What I'm going to say here, I'm going to say the standard size was 100 grams. I'm picking 100 because that's a really easy number to work with. And for starting price, I'm going to go for probably the easiest amount of money I can think of. I'm just going to go for £1. So 100 grams for £1 is the standard. So Jack's idea, how would that affect this standard? Well, he wants to put 25 more cereal into the box and not change the price. So these numbers are fairly easy to work with. So 25% more cereal is going to be 25 grams. So 100 gram plus 25 grams is 125 grams of cereal. But he's not changing the price. So Jack's idea is to sell 125 grams for £1. Okay, so now we need to work out what value for money this gives us. Okay, there's two different ways of working out value for money. So we could either do cost divided by amount, or we could do amount divided by cost. It's a ratio of one against the other. For now, I'm just going to leave it like this. So for £1, it's 125 grams. So now we can think about Sadia's idea. So I'm just going to colour code Jack, which is this. Next, let's think about Sadia's idea. So Sadia's wanting to reduce the price, but to not change the amount of cereal in the box. But she wants her idea to give the same value for money as Jack's idea. Okay, so Sadia, for it to have the same value for money, Sadia needs to offer 125 grams for £1. She wants to be equivalent to that, because she wants to be the same value for money. So we can use this value for money as 125 grams for £1. So this starting amount, 100 grams for £1, we can think of this as a ratio as well. So we're wanting 125 grams to 100 pennies. So we can simplify this ratio here. Both these numbers are multiples of 25. So we could say that as a ratio of value for moneyness, if that's a thing, which of course it isn't, oops, made a mistake, we're wanting 5 grams for every 4 pence spent. That's what Jack's idea is. So here, for Sadia's, we need to do this without changing the 100 grams starting thing. So he wants to keep the box the same. So 100 grams, 100p. So she wants this ratio to be in the form 5 to 4. Okay? So let's think of it this way. So Sadia wants it to be like this, 100 grams for 100p, because obviously that's the same as what... So Sadia wants it to be, this here. That same sort of ratio. But she wants the grams to be 100. So how can I go from 5 grams up to 100 grams? Well, 5 times 20 gives me 100. So to keep it balanced, I do the same to the other side. If I multiply this by 20, I need to multiply the price by 20 as well. 4p times 20 is 80p. So this offer is 5 grams for every 4p. So one way of doing this would be to keep the price as a pound, like Jack. There's a ratio building up, that would be 125 grams for 100p, a pound, or doing it in Sadia's way, where we keep the weight, the mass of the cereal the same. It's the same as offering 100 grams for a reduced price of 80p. So Sadia needs to reduce the price from 100p to 80p. She's knocked 20p off each pound, therefore she needs to reduce it by 20%. Sadia needs to offer a 20% reduction. And the reason for that is 100p needs to go down to 80p, and the percentage change is always based off the original. So based off the original price of 100, 20p gets knocked off. 20p as a percentage of 100, 20p over 100 is 20%. So that's all we need to do for that one. Quite an awkward question, I think, but make of it what you will. You know what, if you're there thinking that was really hard and really awkward and quite ugly, what I've explained it, and to be honest, I'm not very happy with how I've explained that here either, because the method's been quite ugly. What I'm going to do is show you another method now using direct algebra. So if you've not liked that method, hold your horses, here's a different approach. So what we could have done is an algebraic approach for this one. So if we did that, what we need to think about first is, because this question hinges on this notion of what value for money is, what's one way we could define value for money? Well, one thing we could do would be to define it as either the cost divided by the amount, or the amount divided by the cost. Commonly, what would a supermarket define value for money as? Well, I've got this image from a supermarket, and we can see here that it's saying about this chocolate the value for money, which most supermarkets will do. It says here £1 per 100 grams. So they are doing the value for money as the cost divided by the amount. So that's the measure of value for money we can use here. Value for money, VFM for short, is just cost divided by amount. But for this question, as we already know, we're not told what the cost is or the amount of the original cereal. So we can just say let X be the original cost of the cereal, and let Y be the original amount. Now let's think about what Jack's idea is, because Jack is mentioned first. So for Jack, what he wants to do is to put 25% more cereal and not change the price. So the value for money for Jack, so the value for money is cost divided by the amount. So from that, the original value for money would have been the cost, X, divided by the amount, Y. But what Jack's doing is he's taking the amount and putting 25% more into it. And so if we take the original amount Y and increase by 25%, it's the same as doing Y multiplied by an extra 1.25. 25% more as a decimal multiplier is 1.25. So Jack's amount relative to original isn't Y, it's 1.25Y. It's the original amount plus an extra quarter. He's not changing the cost, so the original cost is still the same, but he's increasing the amount by a factor of 1.25, which is the same as 25% more. So that's Jack's value for money. Whereas for Sadia, Sadia's idea is to reduce the price, but to not change the amount. So the value for money for Sadia is she's not wanting to change the amount. The original amount was Y, so she wants that fixed at Y. But what she does want to do is to reduce the price. Reduce it what to, we don't know. So I'm just going to call this here a question mark. So what price is she wanting? Now, what she does want is to have the same value for money as Jack. So her value for money, which is this expression, must be the same as Jack's, which I've highlighted in yellow. So what we can do now is to get an expression. So we can say that x over 1.25y has to be the same as Sadia's value for money, which is some question mark, divided by y. So we've got two fractions which are equal to one another. Now, there's a few ways of doing this question. What I tend to do is to think of this as cross multiplication. So x times y will equal 1.25y multiplied by this question mark. So x times y equals 1.25y multiplied by that question mark. So what we can do here is we can work out what the cost Sadia wants to charge it for by getting this question mark on its own. We can divide both sides by 1.25y. Okay, so therefore, what she wants to sell it for will be xy divided by 1.25y. So you'll see here, because we've got a y at the top and the bottom, the y's will cancel. So it's got x divided by 1.25. Now, what I'm going to do here, I'm going to think about what 1.25 would be as a fraction. Okay, so as a fraction, 1.25 is the same as 5 over 4. So 1.25, that's the same as 5 over 4. If you're dividing by a fraction, that's the same as multiplying by that fraction reciprocated. That's the same as multiplying by 5 over 4 turned on its head. So x times 4 over 5 is 4x over 5. Now we've pretty much got it, so therefore Sadia needs to sell the cereal at 4/5 of the original price. I'll just scroll down so I've got more space. At 4/5 of original price. So we're talking about percentage here though, and percentage change. So what's 4/5 as a percentage? Well, a percentage means out of 100. So 4/5 of 100 is 80%. So she needs to sell it at 80% of the original. So she's gone from selling it at 100% down to 80% to match Jack's value for money. She's knocked off 20% of the original cost, because 100 minus 20 is the 80% she needs to be selling it at. So the percentage she needs to reduce it by, she needs to reduce it by 20%. And that is our final conclusion. She needs to reduce the price by 20%, because 100 minus 20 gives us the 80% she needs to be selling it at. That approach might seem simpler to you. I do think it's quite a hard question anyway, no matter which way you do it. So if that way works better for you, then feel free to stick to that approach. Question 12 is about circle theorems. So as you can see, quite obviously we have a circle, and we've gotten some information about this circle, and all this information has been labelled on the diagram anyway. Importantly here, we need to find the size of angle CA0. Now CA0 means the angle made as we move from C to A, then to 0, so we're trying to find this one here. I'm going to show two methods of this. Both methods are going to hinge on knowing one circle theorem in particular, which is this one. So we need to know in both cases that the angle between a tangent and a chord is equal to the angle in the opposite segment. So for example, if you've got a triangle where all corners are on the circumference, which we have here in terms of A, B, C, then where a point meets the tangent, the angle on one side of that point is equal to the angle on the opposite side of the line in between the tangent and that side, making the angle. So this one is the same as that one, and likewise for the blue angle. So I'm going to show you two main ways. So either is equivalent. So first of all, I'm just going to call this method A. So first off, method A. So what I would establish first of all is that this is going to be a right angle. Okay, because that's a right angle, it's because we have a tangent meeting a radius. Okay, so we could say, for example, OAE is 90 degrees. Okay, so if we wanted to, we could write down the reason for that. So it's tangent is perpendicular to the radius where they meet. Okay, so we know OAE is 90 degrees. From that, we can work out the size of OAB. We can work out this one here, because we know that OAB plus BAE needs to add up to 90 degrees. So from O to A to B, we've got 56 degrees of right angle here. So this is going to be 90 minus 56, which is 34 degrees. Okay, so we can write that down. So we've worked out that O to A to B is 90 minus 56, which is 34 degrees. So where do we go next? Well, there's a few places we can go next. So what we should spot here is that this triangle OAB is isosceles, because both of these sides are radii. So the base angles of an isosceles triangle are equal. So if this is 34, this one here will be 34. Okay, so we might just want to write that down in some form or other. So I'd say we might just want to sketch down that OBA equals OAB, which is 34 degrees. And maybe just state that it's because it's an isosceles triangle. Now this is going to be the key point. We know now that CBA is going to be 69 degrees. So this angle here, CBA, is going to be this 34 plus 35, which is 69 degrees. Okay, and that's fairly self-explanatory. It's just the sum of the 35 and the 34. So I'm just going to colour this in now so we can just see where it's coming from. So the entirety of this angle is 69 degrees. So I'm just going to say here, so therefore the angle at B, so CBA, is 35 plus 34, which is 69 degrees. Now, because of this, we can now use this theorem here. So this green angle, which is CBA, which I've said is 69 degrees, that's in the opposite segment to the angle CAD. So CAD is going to be 69 degrees as well. We're actually using this theorem here on the right hand side of our page. So again, we can state that. So CAD equals 69 degrees because it's the angle in the alternate segment, alternate or opposite. Now you don't need to go to town and write the full wording of the circle theorem down, it will suffice just to put this. Okay, and the reason for that is you just need to show the examiner you know what you're talking about. You don't need to write War and Peace and just fill the page with working, but at the same time do put a little bit of wording in, just so you're evidencing that you do know about the circle theorems. So we're pretty much home and dry now. We've done everything apart from the last stage. So we want to work out CAO, which is just this tiny one in the middle of all the rest that's going on. Okay, and if you notice, 69, CAO, and this right angle are all lying on this tangent from E to D. So we can use the idea that angles on a straight line add up to 180 degrees. So therefore, finally, CAO is going to equal this 180 on the straight line minus the 69 degrees, which is CAD, minus this right angle, which is 90. And so if we calculate this, I think it's probably easy to do 180 minus 90 first. 180 minus 90 gives us 90. Then 90 take away 69, that leaves us with 21 degrees. So angle CAO is 21 degrees, and that's a fairly long-winded question. So that's one method of doing it. I'm going to show you method B, which is very similar, just slightly different. So method B, a similar approach. First thing I'd suggest, again, as with method A, is to just state that the angle OAE is a right angle. Okay, so like I said before, go back a minute, OAE was 90 degrees, so we just copy that down in the same way. So OAE equals 90 degrees, and just give the reason. The reason, obviously, that a tangent meets radius at 90 degrees. So what can we do next? Well, what we can do here pretty much straight away is we can use this idea of the angle between the tangent and a chord being equal to the angle in the alternate segment. So here we spot that this angle here is 56 degrees. Now using the angle in the opposite segment theorem, where's opposite to this one? So the angle completely opposite to this dividing line is actually over here. It's going to be where angle C is. So those two are equal, so we can state that with the ultimate segment theorem. That's 56 degrees. So we say that angle BCA equals angle BAE, which is 56 degrees. And just state that the angle in the alternate segment is equal. So we've got that. So what else can we put down? Well, one thing I'd put here is, again, similar to method B, because this whole angle from here to here is 90 degrees, this one doing in purple will be 90 minus 56, which is 34 degrees. So that's 34 degrees. So I can just write that down. So angle O to A to B is 90 minus 56, which is 34 degrees. And then we can say that's equal to the angle OBA. And the reason for that is it's an isosceles triangle, because OBA or OAB is a triangle made up of two radiuses or radii, here and here. So again, I'm just going to colour code that in. So that's going to be 34 as well. And just like colouring in, really, I'm going to colour this in a green. There we go. So where can we go next? Well, let's have a think about it. What other angle could we work out, or what other angles could we work out? Well, we know that angles in a triangle add up to 180 degrees. So this triangle OAB, we know both these are 34 degrees, so we could work out the angle at BOA. So BOA will be 180 minus 34 minus another 34, or simply 180 minus 68. And that's going to give us 112. So that's 112 degrees. So again, if the working is on the diagram, that's fine as well. So angle around O, well, we should know that angles around a point add up to 360 degrees. And so this angle here around O is going to be 360 subtract 112. Okay, so 0 take away 2 we can't do, so we just borrow 1 from the 6, which becomes 5. One we're borrowing, we move over to that 0, which is now 10. 10 take away 2 is 8, 5 take 1 is 4, and 3 take 1 gives us 2. So this angle's 248 degrees. So but in 360 minus that angle, we worked out that the angle of the other side of the centre is 248. Now what we can do is we can focus in, if we wanted, on the shape BCAO. So if I just get this and label it on with a different colour, just to make it clear. So I'm going to go from B to O, O to A to C, and then C to B. Now it looks like an arrow maybe, but ultimately this is a four-sided shape. We need to know that a four-sided shape, a quadrilateral in other words, the angles inside them always add up to 360. So after all this working, we can say that this angle here ultimately this is the angle we want to find. That's angle CAO. So CAO will be 360 minus these other three. So the angle CAO will be 360 minus 248 minus 56 minus 35. So that's a bit of a calculation to do in its own right. Well, 360 minus 248 is 112. But another way we might want to do it is just to sum all these numbers that we're taking away. So all in all, what are we subtracting? Well, we can add up the total of what we're subtracting. So 248 plus 56 plus 35. 8 plus 6 plus 5. 8 plus 6 is 14, plus 5 gives us 19, so put 9, carry 1 along. 4 plus 5 is 9, plus 3 is 12, plus 1 we're carrying on is 13, carry over 1, then 2 plus 1 is 3, so we get 339. So we're doing 360, take away 339 essentially, which again, as before, gives us 21 degrees. And so there are two different approaches to solving the same problem. Let's now have a look at the next question, question 13. Question 13 describes fully the transformation that maps triangle A onto triangle B. Well, this isn't a bad question really. Transformation means it can only be one of four different things. So what types of transformations do we have? We have rotations, we have reflections, we have translations, and we have enlargements. So a rotation is where the size of the shape doesn't change, but it just rotates around. So here it looks like it's been rotated to go from A to B, but it has changed size, so it can't be a rotation. A reflection, again, is where it just flips over, but doesn't change size. So it's not reflection. Translation, again, the common theme, it doesn't change size, it just seems to move. So because it's changed size, what we have to say is it's got to be an enlargement. So we need to state that it's an enlargement to get any credit whatsoever. So we first of all just say it's an enlargement. What else do we need to say? Well, there's always going to be a scale factor for enlargement, and there's going to be a centre of enlargement. So we can work out the centre of enlargement by mapping each point to each point. So let's start with a right angle first. So this right angle on A gets mapped to that right angle on B. So let's just map those. Okay, so that's like so. Let's have a look now at this other one I've drawn on. So this other one is the larger of the two other angles left. So that's the larger angle there, that's the smallest one, and this is the larger angle on A. So if we map these two to each other, let's just see what we'll get there. Well, we get this. And finally, just mapping this one to that one, what we're going to get here is another line, and what you should notice is we're going to cross. All these lines will cross, and where they cross, that's a special point. This here is the centre of enlargement. So we stated that it's an enlargement. The next thing we state is the centre of enlargement. So the coordinates of this centre of enlargement are 2 and 2. Okay, so we've done that. The next thing we need to consider is the scale factor of enlargement. So first of all, we can see that to go from A to B, the shape has got smaller. So it's quite weird to think of it as being an enlargement when it can get smaller. So all we need to do here is to consider what fraction of the original size it's become. So if I just pick this side here, that's side 1, its original corresponding side had a length of 3. If you wanted to, you could pick this side. That is 2, but it used to be 6. So to go from 3 down to 1, or indeed from 6 down to 2, what have we divided by? Well, the sides have been divided by 3. In other words, the shape is only 1/3 the size it is now. But there's a twist. The twist is the centre of enlargement relative to the original shape. The enlarged shape has popped out the other side. So if we imagine these lines as going towards the original shape, like so, if it were a standard enlargement, this is like, I don't know, a light, the shadow would be down here, probably just to the bottom left of our screen, but actually it's popped out the opposite way. A spot for this is, it looks like it's been almost rotated. So if it's an enlargement which looks a bit like a rotation, that's a clue that it's actually a negative scale factor. It's popped out on the opposite side to the centre of enlargement. So importantly, we need to put -1/3 for our scale factor. So enlargement, always take the centre of enlargement and give the scale factor of enlargement. Each side becomes 1/3 of the size they used to be, but the shape's popped out on the opposite side, so therefore opposite means minus. Question 14a, one I've embarrassingly missed from the first recording, so here it is belatedly. So it's fairly straightforward, luckily, so I won't take too much time. Let's get to it. Work out the value of 16/81 to the power 3/4. So we've got a fractional power. So what we need to realise here is the top number means sort of what power we're raising it to. The bottom number relates to the root. And so what this means is we can think of it as the 4th root of 16/81. And then all of that raised to the power 3. So like I've said, the top number means the overall power, and you can think of the bottom number as the root. So you can think of the fractional power as 2 separate things, a root and a power combined. So before making a number big by doing the power of it, it's probably easier to make the numbers smaller first. So let's try and do the 4th root of 16/81. Now another law of doing roots or powers is if we have a fraction, we can apply this root to the top and bottom separately. So we can do the 4th root of 16 and the 4th root of 81 separately, and then do that to the power 3. Now luckily, as you'll see, these numbers do have 4th roots. So what number to the power 4 would give us 16? Well, 2 times 2 times 2 times 2 would be 16, so the 4th root of 16 is actually 2, because 2 to the power 4 gives us this. In the same way, the 4th root of 81 would actually be 3, because 3 squared is 9, times by 3 again is 27, and 27 times 3 gives us 81. So we can do 2/3 to the power 3, and again, like I've said, with powers or roots, we can do this power to the top and bottom individually. So that's the same as 2 cubed over 3 cubed, and 2 cubed is 8, and 3 cubed is 27. And so that's the final answer to all of that. Does it simplify? No, it doesn't. So we'll just leave it as 8/27. And that's question 4a complete. Question 14, we've got one about indices. So these, we have 3 to the power of different things. 3 to the power a, to B to C, and we need to work out the value of A plus B plus C. So there's no other way around this apart from knowing laws of indices. So if we just focus on 3 to the A first of all. So we're told that 3 to the A is 1 over 9. Now the key thing to notice here is that 9 on the denominator is itself a square number. In fact, it's 3 squared because 3 times 3 is 9. Now, one of the laws of indices, which you may or may not have seen, you probably have if you've been studying higher tier, is that in general, 1 over A to the n is the same as A to the power minus n. So 1 over something to a certain power is the same as that something to that power made minus. So over here, because we've got 1 over 3 squared, our A is like 3. It's to the power 2, so in this case n is 2. So minus n will be minus 2. In other words, 1 over 3 squared is the same as 3 to the power of minus 2. So we can therefore hopefully see that because 3 to the A is the same as 3 to the power minus 2, the base value is the same, 3 equals 3, therefore A has to equal negative 2. So we can note that down straight away. The next one we have is 3b equals 9 root 3. So let's write this down and simplify along where we can. So we have 9 root 3. Well, 9 is 3 squared. And something to the square root is the same as to the power of a half. So the square root of 3 is the same as 3 to the half. To raise something to the power half is one and the same as square rooting it. So that's again another rule we should know about. So we've got the base number the same, both are 3, powers of 3, and we're multiplying. This is another indice law. So a to the power n multiplied by a to the power m. When we multiply with indices and the base values are the same, we simply add the powers together. So as a single power of a, we have n plus m. Okay, so in our case, this is going to be the same as 3 to the power of 2 plus a half. Now 2 add a half is 2.5, and as a top-heavy fraction, 2.5 is the same as 5 halves. If you really want to, you could say it's equal 3 to the power 2.5. Doesn't really matter which one you go for, but the important thing to mention here is that 3 to the power b is the same as 3 to the power 5 over 2. 3 equals 3, that's equal to this, so therefore the powers must be equal too. So b must equal 5 over 2, or if you put it in decimal form, it's equal to 2.5. So we now know that b is 2.5. Finally, we just need to think about c, and c features in this final relation here. So 3 to the c equals 1 over the square root of 3. Now, as I said earlier, the square root of a number is the same as that number being raised to the power of a half. We can then use this relation here. 1 over something to a power is the same as that something to that power made minus. So 1 over 3 to the half is the same as 3 to the power of minus 1/2. Now we can make the same link as before. Both base values are 3, so 3 equals 3, so therefore the base values must be the same as well. In other words, c must equal 1/2. Sorry, minus 1/2, I mean to say. So therefore, we can just finish off the final bit of the puzzle. So therefore, a plus b plus c. So we know what a is, we know what b is, and of course, we know what C is, because we just worked them out in this red writing, the blue writing, and the green writing, respectively. So let's just finish off this calculation. So we said A was -2, B we had was 2.5, and C was -0.5, which I'm going to put as a decimal, which is -0.5. Now, this is where you need to have some conviction in your calculation. So, -2 plus 2.5 takes us up to positive 0.5, then we're minus 0.5. So overall, the final answer to all of this is weirdly but actually equal to 0. So what we have here is this whole thing is equal to 0. Strange but true. A plus B plus C equals 0. Let's now have a look at question 15. So for question 15, we have here that shapes A, B and C are mathematically similar. We have the surface area of A is 4 and the surface area of B is 25. The ratio of volume of shape D to the volume of shape C is 27 to 64. Work out the ratio of height of shape A to the height of shape B. Give your answer in its simplest form. So this is a case of linear, area and volume ratios of similar shapes. Now we need to remember a few key important concepts here. So I'm going to highlight them for you now. So if three shapes A, B and C are similar, then we have the following. So the ratio of their lengths, the length ratio, which could be heights, widths or lengths, is A to B to C. So if we just start with defining the length ratio as A to B to C, then the ratio of areas will be these values all squared. So areas will be A squared to B squared to C squared, and the ratio of their volumes will be A cubed to B cubed to C cubed. And the best approach is to find out the ratio of lengths first. And to do that, it depends where we're starting. So if we're starting with area ratios, for example, here, we can go to this, to the ratio of their lengths, by thinking, how do we go from something squared to something which isn't squared? Well, the way we do that would be to square root. Or it could be the case that we end up with a ratio of volumes of different things. And if we have that, then it's a similar sort of thing we need to do. You can probably guess. To go from area ratios to linear ratios, we square root. To go from something cubed to something just to the power 1, what's the opposite of cubing something? Well, the opposite of cubing something would be to take the cube roots. So that's the key concept. Always try, if you can, to begin with the linear relationship. So let's now consider how we can put this into a table of values. So we can populate a table of values based off the linear ratios as following. So linear ratios only, shape A, shape B, shape C. So just going back to what we had before. So ratio of areas, then we mentioned ratio of volumes, but the objective really would be to have the linear ratios as so. So let's read the question carefully and see that we've got an area relationship here between A and B. So surface area is a ratio of areas. So here we're talking about A squared to B squared. We're talking about area, importantly. So A squared to B squared, the ratio of areas of A to B is 4 to 25. But of course, we want to work out the ratio of lengths. Now, like I said earlier, to go from area relationship to linear relationship, we need to square root. Basically, we just take the square root. So from this, we can work out the linear ratio of A to B by square rooting the above. And if you notice here, the examiner's been fairly nice for giving you a clue, because 4 and 25 are square numbers. So if we square root 4, we get 2, and if we square root 25, we get 5. So we're going from the red to the green, from the areas to the linear, by square rooting the area relationships. Therefore, we can fill in this table. So shape A to shape B is in the ratio 2 to 5. Now, we're mentioned here about volume relationship between B and C. So if you read this bit carefully, the ratio of the volume of shape B to shape C is 27 to 64. So what this tells us is that the ratio of volume of A cubed, to the ratio of volume of B, which is B cubed, is 27 to 64. And like I mentioned earlier, to go from a volume relationship, which is cubes, to a linear relationship, which is to the power of 1, we do the opposite of cubing, which is essentially to take the cube root. So here we can just cube root the 27 and cube root the 64. I apologise, this isn't A to B, it's B to C. I do apologise, I'll just correct this here. So it's B to C, I do apologise. So now what we can do, again apologies, is we can work out the linear relationship by doing the cube root of both sides. So 27 is actually 3 times 3 times 3. So the cube root of 27 is 3 because 3 cubed gives you 27. Likewise, the cube root of 64 is going to be 4 because 4 times 4 times 4 gives us 64. So for B to C, we have 3 to 4. The problem we have here is that we can't match up these into one ratio because we've got shape B, which is 5, and here shape B is 3. So what we need to consider now is, what's the lowest common multiple of 5 and 3? What number is in the 5 times table and the 3 times table? Well, hopefully you can see here that 15 is in both the 5 and the 3 times table. So we can get shape A to shape B to shape C by making the numbers in shape, these numbers here, the number 5, into 15. So what we can do here is we can multiply these numbers by 3. So 2 times 3 is 6. 5 times 3 is 15. Likewise, to go from 3 to 15, we'd have to multiply by 5. So if we times by 5, we'd do here 4 times 5, which is 20. We now have a linear ratio of shape A to shape B to shape C, all comparing like for like. So now we're in a position to answer the actual question. So the actual question is work out the ratio of heights. So heights, again, heights is a linear ratio which you already worked out here. So we just want the ratio of heights of shape A, okay, so shape A to shape C. So because it's all on the same line, 6 to 15 to 20, it doesn't matter that shape A isn't next to shape C. For example, the linear ratio this is, of shape A to shape B is 6 to 15, which is the same as 2 to 5. The linear ratio of shape B to shape C is 15 to 20. Or, from end to end, the linear ratio of shape A to shape C is 6 to 20. So, ratio of A to C, in fact, I'll do it as a question is saying. So it says, ratio of height ratio of A to C. Well, A is 6, as we can see, and C is 20. So we're almost home and dry. It'd be a shame, though, to leave it as 6.20 because, importantly, the answer needs to be in its simplest form. 6.20 is not in its simplest form because 6 and 20 are both even. So we can divide both sides of this ratio by 2 to obtain 3 to 10. And that is in its simplest form. Therefore, the ratio of heights of shape A to shape C is 3 to 10. For every 3 centimeters high shape A is, shape C is 10 centimeters high. Question 16. Prove algebraically that 0.256 recurring can be written as 127 over 495. Now the dots are only above the 5 and the 6. So this means the 2 isn't recurring in the repeating block, just the 5 and the 6 is recurring. So what we're going to say here is we let x or y, or any algebraic letter, equal this thing here. So let x equal 0.256. So what we're saying, and it's helpful, I believe, to write out this repeating block a few times so we can get the pattern in our heads clearly. So x equals 0.256565656 on and on and on to infinity. Now, alternatively, this is an option. I'm going to do this so it's easier to see how it's set out. I'm going to do this here in terms of blocks so we can see clearly how the numbers line up. And what we're trying to do is we're trying to go for wiping out, when we subtract one from the other, these repeating blocks. Okay, so that's what we have. So the decimal's there, which is quite hard to see now, so I'll just put the decimal in a big red dot. What we next do is we multiply x by tens until we get a repeating block lining up nicely. So for example, here we can multiply everything by 10. So if that's x, what would 10x equal? Well, what would happen here is essentially it would look like every digit just hops to the left one number. Or alternatively, it looks like the dot would move back by 1. But keeping this dot fixed and moving each number to the left by 1, that would give us 2. That 5 would hop over to this side. That 6 would move on over. That 5 would move over. That 6 would move over. And now hopefully you can see the repeating pattern. 5, 6, 5, 6, 5, 6. Now, do those numbers line up nicely? Do we have the same numbers directly beneath each other? No, we don't. Where there's a 5, there's a 6. Where there's a 6, there's a 5. So that doesn't work. But don't worry, all we need to do now is to go again. So we multiply by 10 once more. So 10x times another 10 gives us 100x's. Move these digits to the left once again by 1 place. So that 5 will move along 1. So rather than being just a 2, we'll now have 25. So that 5 moved to the left. That 6 will now move to the left. So 6 moves 1 over here. That 5 will move to the left one. So the 5 will go there. That 6 moves over. That 5 moves over. So again, now we have 6, 5, 6, 5, and so on and so on. But now let's compare the original x to this 100x. Do the numbers at some point, I mean, not necessarily straight away, do they line up? 2 here, 6 there. No, they don't. But look to the right. Here there's a 5, down here there's a 5. Then there's a 6, here there's a 6. Now actually here the numbers do line up nicely. 5, 5, 5, 5, 5, 5. 6, 6, 6, and 6, 6, 6. Don't mean to sound evil. 6, 6, 6, whatever. Anyway, silly joke. So now what we can do is we can do one subtract the other. So what I'm going to do now is I'm going to take 100x's and subtract 1x from this. So if I were to do that, just move this x down here like so. I can now do one massive subtraction. So I'm just looking now at 100x's minus 1x. If we do that, obviously 100x's take away 1x, that'll just leave us with 99x's. So 99x equals what? Well, obviously we know when we subtract, we start from the right. There's no real right-hand side to start from because this goes on forever. But as you can see here, 6 take 6 is nothing. 5 take 5 is nothing. There's an infinite amount of cancellations here. Nothing, 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 until we get to this stage here. Now they don't match, but that's fine. But ultimately, the repeating pattern will cancel itself out perfectly. Now we've got 6 take 2, which is 4. And here 25 take away nothing is just 25. So we've got 99x equals 25.4. We want to work out what x is. We want to show that x is equal as a fraction to 127 over 495. So what we can do here to both sides is divide both sides by 99. And if we do that, we'll end up with x on its own, which is our objective. So therefore, x will equal 25.4 divided by 99. Doesn't exactly look like this though yet, does it? But hold on, because we can get it to look like this. So if you notice here, these are both whole numbers, no decimals. So what could I multiply this by to get it to be a whole number? Well, I'd suggest what we can do is just multiply by 10. So if we multiply the top and bottom of this fraction by 10, okay, what will we have? Well, the top, 25.4 times 10, that dot will just move one place to the right, which will give us 254. On the bottom, 99 times 10, that'll give us 990. Once again, I'm running out of space, which is something I always do, which is something I never seem to learn. Anyway, that still isn't the same as what we're trying to prove. However, look at these numbers. Both are even. So we can divide top and bottom by 2, because any even number can be halved. So 254 halved, well, half of 200 is 100. Half of 54 is 27. Likewise, if we half this, if you're not sure, you can just do it the slower way, which is fine, by doing long division. 2 into 9, we can fit 4 of them, because 2 times 4 is 8. That leaves us with a remainder of 1, which goes there. That 9 is now 19. 2 into 19, well, we can fit 9 2's into 19. 9 times 2 is 18, which is 1 away from 19. So the remainder is 1. Finally, 2 into this 10 gives us 5, and we're done because there's no remainder. So in other words, half of 990 is 495, and if you now look, this is what we wanted to prove all along. So x, which we defined as being this, is one and the same as 127 over 495. So we've proved it algebraically with this infinite cancelling trick here. So that's the final answer, and we're done with question 16. Question 17, we have a quadratic curve. A bit of a puzzly type question here. So we've got the equation of a curve is x squared plus ax plus b, where a and b are integers. So we're told they're basically whole numbers that might be negative. So we're told the points 0, -5, and 5, 0 lie on the curve. So let's just add these in now. 0 minus 5 is just essentially telling us the y-axis intercept. It's saying when x is 0, y is -5. Likewise, this point here is telling us when x is 5 that y is 0. So find the coordinates of a turning point. So we can use this one here and substitute it into this equation. So when x is 0, y is -5. So let's sub this into here. So we've got y being -5, and in this case x is 0. So let's see what this gives us. So we've got -5 squared. Sorry, what am I talking? No, we haven't. We've got -5 on its own, my apologies. So -5 equals, well, x is 0, so it's going to be 0 squared plus a times 0. 0 lots of a plus b. 0 squared is nothing. 0 lots of a is nothing. In other words, we've worked out that b has to be -5. So we can now use this in the next step. So when x is 5, we're told that y is 0 from this point here. So we just sub these values into this equation. So y is 0, so 0 equals x squared, which is 5 squared, plus a times 5, because x is 5, a times 5 is the same as 5a's, plus b, but we worked out from this part that actually b is -5. So that's the same as plus -5. So of course we can neaten this up. So 0 equals 25 plus 5a, take 5. Magically changed colour there, that was quite strange. So let's change it back into the black. So 25 minus 5 is 20. So if I just take this 20 and subtract it from both sides, we get -20 equals 5a. Therefore, dividing by 5, a must be -4. So this equation is therefore y equals x squared. A is -4, so plus ax is the same as -4x. And likewise, b is -5, so that's the same as saying plus -5, which is just obviously -5. Now, we can find the turning point essentially by completing the square on this. So if we complete the square, we can swap this expression x squared minus 4x for its completed square alternative. So x squared minus 4x, instead of an x squared, we put the x in brackets. We half the coefficient of the x, the number in front of the x, so we half minus 4, which gives us minus 2. We square that, and then when we complete the square, we always subtract the value of this second thing squared. Minus 2 multiplied by minus 2 is positive 4, so we subtract 4. So all we're doing here is we're essentially replacing this with that. And let's not forget the minus 5. So this gives us x minus 2 squared minus 9. We now can see the turning point of the curve. And I'm going to explain why, in case you've not seen this before. Okay. This turning point, all it means is whereabouts the graph is at a minimum or maximum, the bottom point here. So what value of x would minimize y? Well, anything squared has to be positive, doesn't it? You can't square something and get a negative. So y is going to be minimized when this thing in brackets, which we're squaring, is as small as possible. So what value of x would make x minus 2 as tiny as possible? Well, if x was 2, that'd give us 0, wouldn't it? And then 0 squared is 0, which is as small as anything squared could possibly be. So x being 2 would minimize this thing in brackets squared. So when x is 2, that'll be when we have a minimum. When x is 2, we get 2 minus 2 all squared, which is 0 squared, which is 0. So y would then be nothing squared, nothing, minus 9. Nothing minus 9 is minus 9. With enough practice, you can just see, if you've got it in completed square form, the coordinates of the turning point is this number here with its sign switched. So minus 2 becomes positive 2 for the x value. And this number at the end, minus 9, we just stick on, and that's the minimum y value. So the turning point, the coordinates of it, are 2 and minus 9 for y. And that is all we need to do for that one. So the turning point, when x is 2, y, down here would be minus 9. Question 18. We have a graph of a function y equals f of x, which is shown on the grid below. On the grid above, we need to sketch the graph of y equals f of, in brackets, x minus 2. So what's happening here is that the x values, it looks like we're going to take away 2 from each of them. But because this minus 2 is inside the f bracket, it's inside the bracket that comes immediately after the f, we need to remember, inside the function brackets, we do the opposite to what common sense would tell us. Okay? So instead of taking 2 off each of these x values, what we actually do is we add 2 onto them. So I'm just going to trace over this as a cheat. I'm not very good at tracing, as you can see. That'll do. So this graph here is just going to move 2, not to the left, not going to minus 2, we're going to add 2 on to these x values. So what we're going to do here is this whole thing is going to move 1 unit. Oops, let's undo that. So the whole thing is going to move 1, 2 units along, and will end up being here. So it's going to cross the x-axis at 2 and 4. As a double check, you can try what f of 4 would be. So if we've got f of x minus 2, if we input 4, that's the same as f of 4 minus 2. So f of 4 is the same as f of 2, which is 0. So it does work. It's a bit of an odd thing to get your head around. The main thing is inside opposite. It affects the x values in an opposite to common sense way. Rather than subtracting 2 for the x values, we add 2 on. The whole graph just moves 2 units to the right. Let's now have a look at part B. Part B, we've got 2 graphs, graph A and graph B. Now hopefully you can see fairly clearly before we even start to talk about this. Graph A and graph B are a reflection of one another in the y-axis, the reflection in this blue line. So the equation of graph A is y equals g of x. Write down the equation of graph B. Well, if it's a reflection in the y-axis, let's just think about this. There's a quick and easy rule for it, which I'll explain in a moment. A reflection in the y-axis is just that the input, x, has been switched to the opposite sign. So if graph A is y equals g of x, then graph B is y equals g of minus x. That's one of these quick and easy rules. To go from f of x to f of minus x, or from g of x to g of minus x, it's a reflection of the function in the y-axis. And again, if you look here, the change happens inside the brackets. So rather than x being multiplied by 1, we can think of each x value being divided by minus 1. And if in doubt, just let's pick a fairly easy point. So for graph A, okay, that point here is 1 minus 3. But on graph B, the y value has stayed the same, yeah, so the y value is still minus 3 down here. But the x value has become minus. So the y values don't change, but each x gets mapped to its opposite counterpoint. And you could try it for another one as well. You could try it for as many points as you wish. So for example, if I were to take, I don't know, this point here, very roughly, that to me looks like minus 3 and about 1.5 up, approximately. On the other side, again, the y value is still 1.5, but the x value has been made its exact opposite. It's minus of itself here. Minus minus 3, it's plus 3 here. So we just switch the x for a minus x. Graph B is y equals g of minus x. So question 19, we have some function notation. So we've got 2 functions, f of x, which is x plus 1 all squared, and g of x, where we take the input, take 1 away from it, and then double it. So we need to work out g of f of x. We need to show, sorry, that g of f of x equals 2x brackets x plus 2. So when we do this, we start with the inside and work backwards. So g f of x means we do the function g on the input, which is f of x. So what does g do? Well, g takes an input, puts it inside brackets, knocks 1 off it, and then times it by 2. So here, the input of g isn't x, our input for g is f of x. So the way this works is we're going to input f of x instead of this x. So this is going to give us 2 lots f of x minus 1. But of course, what is f of x? Well, we're told what f of x is. F of x is x plus 1 all squared. And so this is 2 lots of x plus 1 all squared. Minus 1. Because f of x is x plus 1 all squared. So then we just have to carry on and have faith that we will arrive at this, what we want to show. So let's expand out x plus 1 all squared. So if we do this, we multiply the first thing, so by itself, so x times x is x squared. We multiply both things in the brackets together and double, so x times 1 is just 1x. Double it gives us 2x. And finally, 1 squared is positive 1. But of course, it's all of that minus this 1. So that gives us just 2 lots of x squared plus 2x. The plus 1 and the minus 1 cancel nicely. So if we now expand this out, 2 multiplied by x squared gives us 2x squared, and 2 multiplied by 2x gives us 4x. But now we can refactorise this. So what's common in both 2x squared and 4x? Well, both numbers are factors of 2, so both are multiples of 2, so we can factorise out a 2. And as well, we have an x in each term, so we can factorise out an x. That's all that's common in each of these terms, so then we open up the brackets. So we've got 2x, we want to end up with 2x squared. So we say for 2x, I need to multiply it by an extra x. Plus sign, so stick a plus sign in. So far we've got 2x, we need to end up with 4x. So what do we multiply 2x by to get the 4x? We need to multiply it by 2. And that, if we have a look, is actually what we wanted to prove all along. So we've done the proof bit. We've shown that g f of x, change the colour of that actually to a nice blue, I think blue is quite nice. So we've shown here that g of f of x, which is this thing, is the same as that. So we've proven what we wanted to show. Now let's have a look at part B of this question. Part B, we're asked to find g minus 1 of 7. What this means is we need to find the inverse function of g of x. So first of all, it's probably easier if we expand this out. G of x is 2 times x, which is 2x, and 2 times minus 1 is minus 2. So how do we arrive at g of x starting with x? So we start with x. The first number to interact with the x is this 2, which multiplies the x. Now we've got 2x. Then obviously we need to subtract 2. So let's just run this by you. So x multiplied by 2 gives us 2x. Then we minus off 2. So that gives us 2x minus 2, which is what g of x is. We can now rewind this to find out what the inverse function is. G minus 1 doesn't mean the reciprocal of g, it just means what's the inverse function of g of x. So we start at this end with an x and go the opposite way, doing the opposite things. So opposite of minusing 2 is add 2. Opposite of multiplying by 2 is dividing by 2. So what does this give us as a full output? So x add 2, like so, and all of that's divided by 2, so it's x add 2, all divided by 2. And that is what g minus 1 of x is. So in other words, g minus 1 of x is x plus 2 over 2. We don't want to work out what g minus 1 of x is. We want g minus 1 of particularly 7. So all we need to do here is just switch the x for a 7. So g minus 1 of 7 is now 7 plus 2 divided by 2. 7 add 2 is 9. And 9 divided by 2 gives us 4.5. And that is g minus 1 of 7. The answer is 4.5. Next we have question 20. So again, this is a show that question. So we need to show that root 18 plus root 2 all squared all over root 8 minus 2 can be written in this form here, where a and b are integers to be found. So first of all, what we can do is we can take this and expand the top. So first of all, root 18 plus root 2 all squared over root 8 minus 2. I did this in a red line. I'll change it to a black line, I think, so it's less scary. So first off, we can expand all this on the top. Okay, if we do that, root 18 times root 18, well, that gives us 18. Now, we can do root 18 times root 2. Root 18 times root 2 is root 36, and then we double that. So we have 2 lots of root 36. If you're thinking, isn't root 36 a square number? Well, it is. I'm going to come to that in a minute. I'm just showing it step by step first of all. And then what we do is we then do root 2 times root 2. Root 2 all squared gives us 2. And that's all over root 8 minus 2. Now this top bit we can neaten up. And so if you were thinking root 36 is 6, well, you were right. So this becomes 18 plus 2 lots of 6. 2 times 6 is 12. 18 plus 12 is 30. Plus 2. The top becomes 32. And that's all over root 8 minus 2. But if we look here, we want to leave it in this form. So in other words, we don't want to have any fraction. We don't want to have any denominator. What we need to do in this step, which you might have seen, is called rationalising the denominator. So what we need to do to both the top and the bottom is we multiply by the conjugate of the bottom. All this means is we keep the things the same. So we keep root 8 and the 2, but we just switch that sign. If this was a plus, it would become a minus here. Because it's already a minus, we change this to a plus. So we multiply both top and bottom by root 8 plus 2. So what that gives us on the top, we have 32 multiplied by root 8 plus 2. And the bottom, we actually get a difference of 2 squares. So root 8 minus 2 multiplied by root 8 plus 2. Well, root 8 times root 8 gives us 8. And minus 2 multiplied by positive 2 gives us minus 4. So the bottom becomes this now. So we have 8 minus 4 on the bottom, which is 4. So this here, 32 divided by 4, that simplifies to 8. So we have 8. Then we have here 2 plus root 8, but we can do better with this. So root 8 we can actually rewrite as the root of 4 multiplied by the root of 2. Because 4 times 2 is 8. And that's all with 2 added onto it. Now, of course, the square root of 4 is 2. So that becomes 8 brackets 2 root 2 plus 2. But now inside the brackets we can see we've got a common factor of 2 in here and here. So we can factorise out that 2 again. So bring that 2 to the outside so it joins the 8. So now we have 8 times 2, which is 16. And then we have root 2 plus 1. Writing it in this form though, with the number on its own first, gives us 1 plus root 2. And that's our final answer for question 20. Question 21. Now, before I begin question 21, I don't mind admitting I found this probably the hardest GCSE vector question I've ever encountered. I do find this hard to explain in a very clear way because I think it's so hard. The quickest and the best way I found to explain it I'm going to give you here. So we're told that from O to A is vector A. So I can label this on straight away, okay? So from O to A, we're told that's vector A. So I'll label this as so. We're also told that from O to B is vector B. So let's just label this on clearly too. And we're also told that the ratio of OP to PM is 3 to 2. So basically, this just means that OP, 3 parts to 2 parts, that's 5 parts in total. So from O to P is these 3 parts of 5, it's 3/5 of the way from O to M. I need to work out the ratio of ON to NB. So where to begin really? I mean, what we can do here, we're mentioning point P twice, OP and PM. So a clue is, can we work out what OM is, and then from there can we work out what OP is? Well, we can, luckily. So from O to M, how can we get there using what we know? Well, from O to M, we can go from O to A, and then we can go, once we're at A, we can go from A to M. Now, what is from A to M? Well, we're told that M is the midpoint of AB. Okay, so from A to M, that's just half of from A to B. Now we know the roots, we can complete this with vectors. So from O to A, that's vector A. Then we've got half of as we go from A to B. So how can we go from A to B using the vectors we know? Well, if we're at A, we can go from A to O, which is along this vector A, but the opposite direction. So that's minus A. And then, once we're at O, we can go from O to B, which is along vector B. So if we expand this out and simplify, O to M, A plus half of minus A, well, I'll expand it out first actually. So I've got A minus a half A plus half of B, A minus half A, that's half of A plus half of B, so that gives us half of A plus B. So that's what OM is. Now how about from O to P? Well, we're told that OP, well I've told you really, OP is 3/5 of OM. So therefore, from O to P, should include a vector symbol there, so OP is 3/5 of the distance from O to M. So it's 3/5 of half of A plus B. Three-fifths of a half, to work out a fraction of a fraction, we times the tops, 3 times 1 is 3, times the bottoms, 5 times 2 is 10. So OP is 3/10 of from A add B. So that's what OP is. Next, what we can consider is, because we know how we can get from O to A, and we know how to get from O to P, what we can next do is work out what from A to P is. Okay, so from A to P, let's consider this next. So from A to P, well, I'm just going to colour code the fact that we know what OP is, because that's going to be useful to us later. From O to P, that's 3/10 of A plus B. To get from A to P, we can do this in two steps. We could go from A to O, then we could go from O to P. I'm trying to put a equal sign there. So A to O, and then from O to P. Now, from A to O is the reverse of vector A, so that's going to be minus A, then plus OP, which is 3/10 of A plus B. So minus 1A plus 3/10 of an A, that's minus 7/10 of an A, plus 3/10 of a B. Now let's compare AP with if you went all the way from A to N. Well, to go from A to N, we'd need to again go from A to O, and then we'd have to get from O to N. So from A to O, like we said earlier, that's minus A. And then O to N. From O to N, that's along vector B. So I'm going to call this just some multiple of vector B. So I'm going to call that plus k lots of B. So from O to N, I'm calling that k lots of B. Essentially, it's just this portion. It's just that portion of the line of vector B. The next thing we need to consider is that AP, which we've worked out is this here, minus 7/10 A plus 3/10 of a B, we need to realise that actually AP, which is this, that's just actually a fraction of the whole distance from A to N, because AN is parallel to AP. So AN is just AP multiplied by something. So what we can say is, what do we need to multiply AP by to get AN? Okay, this purple is just a fraction of AN. So let's compare AP to AN. So compare these two. Compare the purple to this. So obviously KB is a mystery, so I can't compare the B components. However, I do know that this proportion of the A component is minus 7/10, and it's gone here to minus A, so it's gone to minus 1. So what have we multiplied minus 7/10 by to get to minus 1? Well, let's just think of this. So minus 7/10 times what gives us 1. Minus 1, I should say. Because we've gone from minus 7/10 of an A, at AP, to minus 1A for the full distance from A down to N. So obviously minus 1 it's not a fraction, is it? So it has like no denominator. So what I need to do here is I need to multiply this 10 on the bottom by a 10 on the top, which gives me minus 7. And then what I'd need to do would be to divide by 7. So 10 times 10 on the top would cancel. And on the bottom, if I divide by 7, that 7 will cancel with that one. And so it's basically just for a reciprocal without the minus. 7/10 times 10 over 7, 10 there cancels, 7 there cancels. So I must be multiplying by 10 over 7. So therefore, k will be 3/10 multiplied by 10 over 7. Therefore, this multiple k will be 3/10 multiplied by 10 over 7, because we've established what we've multiplied AP by must be 10/7. So I can write this in here. So 3/10 multiplied by 10/7 10 and 10 cancels, so k must be 3/7. So in other words, k, this proportion of b, this must be 3/7 of b. So this blue is 3/7 of b. Therefore, this other bit here, that must be the other 4/7 of b. So therefore, the ratio ON to NB, we've established that from O to N is just 3/7 of B, and NB must be the 4/7. So if I just multiply both sides of this ratio by 7, I get that ON to NB must actually be 3/4. So that is a fairly horrendous, in my humble opinion, vector question. If you can understand all of that, I think you're doing rather well indeed. That isn't particularly straightforward by any stretch. From ON to NB is 3/4. Finally, we finish off with the last question on the paper, so let's have a look now. Question 22. We're told there's only green pens and blue pens in a box. Okay, so let's just think of green and blues. Now this line here is going to be crucial. There are 3 more blue pens than there are green pens. So the number of blue must be the same as the number of green plus 3. So B equals G plus 3. So therefore, the total number of pens is the blue ones, B, which is G plus 3, plus number of green pens. So total pens is B plus G. The number of blue plus number of green is the total number of pens. But we've been told that the blue pens is G plus 3, plus of course the green pens. So the total number of pens is G plus G, which is 2G plus 3. Okay, so the number of blue is G plus 3. Number of green, I'm just going to call that G. Total number of pens is 2G plus 3. We're told there's more than 12 pens in the box. That doesn't seem to make any sense here, but it will do later. Simon's going to take at random 2 pens from the box. The probability that Simon will take 2 pens of the same colour is 27 over 55. Work out the number of green pens in the box. So first of all, we need to work out what's the probability of picking the same colour. Well, there's two ways that can happen. It's a probability of blue then blue. That's one way it could happen. Or, so plus the probability that the first is green, and then the second pick is also green. So, the probability of picking blue and then blue, algebraically, how many blue ones are there? Well, we've got G plus 3 blue. So picking the first blue is G plus 3. And that's out of a total initially of 2G plus 3 pens. So we need to pick blue the first time, and then, so and with probability works as a multiplication. So and then you need to pick a second blue. One blue is now gone, so we'd have only G plus 2 blue left to pick from. And that'll all be over. The total number of pens now is not saying the pen's been replaced. So if it were 2G plus 3 to begin with, there'll now be only 2G plus 2 total pens left. So that's the probability of picking a blue, then a blue. So, or it could be green, then green. So the chance of picking a green first would be the total number of green pens, which is G, pardon me, over the total number of starting pens, which is 2G plus 3. And then we'd have to pick a green the second go too. So to pick a green on the second go, if we pick a green first, so the second picking will be one less green, which is G minus 1. And then there'll be one less pen in total. So 2G plus 3, take one off that, that gives us 2G plus 2. So what we can do here is we can neaten this up somewhat. So if you notice, the denominator is the same for both. So the denominator is going to be 2G plus 3 all over, so multiplied by 2G plus 2. So for the top, for the blue, we've got G plus 3 times G plus 2. Like I say, because these denominators are the same each time, we can put them all under this common denominator of 2G plus 3 times 2G plus 2. And for the green, G times G minus 1 is just G times G minus 1. Now, what I'm going to do here is I'm going to expand out of these brackets. So, on the bottom, what we're going to have is 2G times 2G. That's going to give us 4G squared. 2G times 2 is 4G. 3 times 2G is 6G. And 3 times 2 is 6. And on the top, if we expand all this out, G times G for the blue gives us G squared. G times 2 is 2G. 3 times G is 3G. So in total, we're going to get 5G. And 3 times 2 is 6. And over here, for the greens, G times G gives us G squared as well. And G times minus 1 is minus G. So what we can say here is, well, for definite, we can neaten this up. Okay, so let's just simplify this. So on the top, G squared plus G squared, that's going to give us 2G squared. 5g minus a g, that gives us just plus 4g. And then we have a plus 6. On the bottom we have 4g squared. 4g plus 6g is 10g. And again we have plus 6 at the end. And what we're told all this is going to be equal to, we're told that all this is equal to 27 over 55. So we can set this equal to 27 over 55. So we've actually done the hardest part. The rest now is just to see where we can go with this. Now, one fraction is equal to the other, so I'm just going to take this and make this a bit bigger, just for the sake of making it clearer. So we've got 2g squared plus 4g plus 6 all over 4g squared plus 10g plus 6. Now, before I say it's equal to 27 over 55, which it is, it's worth spotting that we can half both top and bottom of this fraction to make the numbers easier. Okay, so at the top we have g squared plus 2g plus 3. And on the bottom we have 2g squared plus 5g plus 3. And like we know, that's equal to 27 over 55. Now, we've got one fraction equal to another. The way I think about solving these is cross multiplication. So this here, multiplied by 55, must equal this on the bottom, multiplied by 27. So, therefore, 27 lots of the bottom, 2g squared plus 5g plus 3, that will equal 55 lots of the top, which is g squared plus 2g plus 3. So now it's a case of just preparing ourselves for an absolute mess, but having faith that if we've not made a mistake, this will have to simplify. So if we expand this out, 27 times 2g squared, that gives us 54g squared. 27 multiplied by 5g gives us 135g. And 27 multiplied by 3 gives us 81. On this side, 55 times g squared is 55g squared. 55 times 2g, that's 110g. And 55 multiplied by 3 gives us 165. So what I'm going to do now, I'm going to set it into a standard quadratic and get everything over to the same side of the equation. So what I need to do here is to subtract all of this from both sides. So I'm going to subtract 54g squared and 135g and 81 from both sides of this equation. Again, it looks an absolute mess, but have faith it's going to work. It's an absolute mess and looks a nightmare because the last question on these papers is pretty much always evil. So, like I say, take away everything from this side, that leaves us with 0. Over here, 55g squared minus 54g squared just leaves us with 1g squared. 110g minus 135g, that leaves us with minus 25g. And 165 take away 81, well, that will just leave us with 84. Now, have faith, will this factorise? Can we think of two numbers that multiply together to give 84 and add up to 25? Minus 25, apologies. Well, let's just think of number pairs for 84. So 1 and 84. We can make those both minus. They're not going to sum to minus 25. 2 and 42. Still no chance. I could try 3 and 28. Nope. How about 4 and 21? Well, if I make both of those minus, well, that'll actually work, won't it? If I make both of these negative, I've factorised it. Bingo! So this will factorise into g minus 4 and g minus 21. So 0 equals that or that. So therefore, g equals 4, because that'll make this bracket equal to 0, or g equals 21. So it looks like we have two choices, but we need to remember what we had at the start of this question, this absolute beast of a question. We were told at the very start that there's more than 12 pens in the box. And of course, there's 3 more blue than there are green. So if we had 4 green pens, we'd have 7 blue ones, but 4 plus 7 is 11, which isn't more than 12 pens in total. So what we do is we reject this one. That's not possible. That would give us a total of less than 12 pens. Therefore, the total number of green pens must be 21. So to make it clear to the examiner, just say, therefore, there must be 21 green pens. And just double check, we wanted the number of green. Yes, we did. Therefore, like I've said, we do have 21 green pens. So that was a very long solution video for that paper. Quite a few questions were very tricky there. I'll leave it like that. Please do feel free to subscribe in this bottom right corner. I do appreciate you watching. I do hope it's useful to some extent. The timestamps might help. I don't expect you to watch a 3-hour plus video. I just want to try and do it in as much detail as I can without making it too dry. Thank you again anyway, like I say, for watching. Keep your eye on the channel. I'll put some more videos out in a moment, or as soon as I can anyway. Stay safe, and I'll see you all soon. Goodbye for now.